And thanks. I love this ordering. It's great to have like, back-to-back GraphRag talks because one of the things you'll learn about GraphRag as you get into it is that the first steps, seem maybe a little bit intimidating. There's a lot to learn, and there is a lot to learn because there's many different approaches within under the big umbrella of GraphRag. But you're in good company. There's a lot of people that are exploring this space right now, and also in part of my talk, the theme of my talk really is that GraphRag is composable, and as developers, composability is something that's really important to us. And it's true of GraphRag as well. You can start a little bit at a time, and over time get into the bigger, more complicated patterns, perhaps. Along the way, picking the things that make sense for what you're trying to get done. So let me hop right into that. And so this is going to be about composable AI, GraphRag on OPEA. And I'm going to start, if I can, okay. I'm going to start with the idea of composability itself. And we're going to talk about magmas. Magmas, you say? Yes, magmas. Magmas, the math concept. No other acronyms accidentally, brought into here into this talk. A magma is a mathematical structure. It is the basic structure of composing stuff. As a mathematical structure, it's really a pair of two things. There's M and the star here as I'm designating it, where M is some set of things, and a star is just a binary operation on those things. So that if you have some M, you apply the star to another M, you get yet another M. That's the basic idea of composition, and that's called a magma. You're probably familiar with this in other forms. We've all seen this, actually all the time. Whenever we think about composition, this is the kind of the formal way of thinking about it. But let's go through some kind of everyday examples of this. And part of my goal here, again, is to get you to think about composition generally and how simple it can be and also how diverse it can be. And that leads to really, wonderful outcomes. A classic magma is the magma of addition, the addition magma. So if that star is just addition and we are operating on integers, then 1 star 1 results in 2. You've got integers, you return to an integer. That's a magma. It doesn't have to be numbers, though. That's the very mathematical way to think about it. You could take paint colors. You could take some red paint and some blue paint. And if you apply the binary operation of mixing the paint together, you would get purple paint. You still just have colored paint. So this would be the paint magma. A little bit closer to developer home, you can do things with Legos. If you just have some Legos and you combine it with some other Legos by connecting them, so if the binary operation is connecting, you still have Legos. And you've gone from Legos plus Legos equals more Legos. Still Legos all the way down. It's a Lego magma. For functional composition, this is a very common thing that if you're a fan of category theory, you'll see this kind of thing come up all the time. Functional composition, both in functional programming and in category theory, looks like this, where if the things you're composing are functions, where each of those functions have the type takes in a t, returns a t, and you compose them together, you still end up with a function that is taking in a t and returning a t. So composing f and g together, you can denote it like this, like, in the nested function style. And now you've composed two functions, created yet another function. This is the function magma. But we can also do this with data. If you happen to be living in a world of tables, you can combine those tables. We know how to do this. We've done this. Probably all of us have done this at some point in our lives. I don't do it as much these days because I work with graphs. But if you've got a table of some countries and a table of some people that maybe live in those countries, you could do a join on those and find the people that live in those countries. You could join that together. So tables under the join binary operation produce more tables. Tables and tables gives you more tables. This is also true about graphs, though. This is one of the, I think, beautiful aspects of a graph that you can compose your graph under a union operation. There's other compositions that are possible, but you can have a graph magma where you take two graphs, and if they have this red node here in common, you still get a graph. And that's lovely. And it's a little bit different in nature than just combining two tables together. When you get two tables together, you just have yet another table. Okay, it's still in the class of tables. With graphs, you actually end up extending the structure. It's a little bit closer to like what happens when you're composing Legos And you would maybe say that the tables are a little bit closer to what you're doing when you're mixing paint together, in my mind. And of course, these days you can't not talk about AI, so we're going to talk about composing agents. You can also compose agents. And if you had two agents and you compose them with the collaboration operation, you would get another agent that has got two agents inside. It's agents and agents together produce more agents. It's agents all the way down. And since we're talking about OPEA and the wonderful microservices architecture that it offers, you can compose that as well. If you have two services and you orchestrate them together, you just basically have a giant service with services inside of it that all operates together to achieve some goal. The whole point of Magmas is to think about composition in general. That composition is a normal thing, that we do this in everyday life. Actually, we do this when we're making salads. We can do this when we're writing code, of course. We do this when we're building. And as software developers, we're used to doing composition. We do this in software all the time. We take objects, we combine them together to create yet another object. All kinds of great design patterns around this. So we also know that once we've figured out a particular rule of composition, and for any given set of things, it's not just that there's one way of combining them. You can think of different binary operations that take these two things together and produce a third thing that is still of the same type. That lets you both, think about how you can build up things, but also it gives you the ability to decompose, which is something we do all the time in developing software and also in managing data. That we think about, like, what is the overall structure? How can we break that down to make smaller structures that are still themselves useful? And because lots of different things can be composed, AI itself can be composed as well. All the sort of natural skills we have as developers, we can apply towards AI. And one of the lovely aspects of being able to do composition, and I guess I'll credit AI to this for sure. It's made it very obvious that when you repeatedly compose things, there are emergent features, things that weren't obvious when you first started doing the composition. You might have started with, like, small bits of Legos, but over time, as you build more and more together, it's not just that you have bigger sets of Legos, you actually have emergent features within the Lego set. Oh, and apparently I've skipped a slide there, so let me just dwell on that for a second. So, with Legos, you start composing Legos together. You go from just some blocks to maybe you've built a house, maybe you've built a mansion, maybe you've built the Millennium Falcon. The same is true for anything that we compose, that over sort of scaling time, it starts like really small and you can't really quite see necessarily what the forest looks like because you're looking at the trees. But the more that you add together, things start to evolve. And this happens in graphs as well, that on a very small scale, graph composition starts with just having nodes, and you combine those nodes together to have, a new graph structure. Nodes themselves are already totally valid, graphs. And so you could put them under the composition of relating them, and then actually you get, another structure out of that. And as you continue to compose a graph together, you go from individual things to neighborhoods of things to entire communities of things on kind of a social level. You can think of an analog here that this goes from, an individual to the family that you know, to the neighborhood that you're part of, to a community, to a society, to the entire global world, all built through individual relationships, individual people, but then have emergent behaviors at different scales of the connections. The same is true in data if you're working with a graph. And I want to think about that in one other angle than this whole idea of how things over scale change and why that's particularly interesting for graph. I'm sorry, for graphs in RAG. And I think about the information value of doing RAG in the first place. In the previous talk, I mentioned on this, actually at the end of it, there was a bit of a question around this, thinking about vectors, of course. And let's pause it for a moment though. Like if you have some collection of chunks or records, and let's say that, for each chunk or record, the value of that record is that it can answer one question. And maybe maybe it answers more questions, but generally, like, let's think about it a simplified way, that there's a one-to-one relationship for every chunk of thing you've got, there's one thing you can answer. And so the value then is linear. There's like number of chunks you have, and the value then of the overall data set is directly correlated with that. So if you've got 10 chunks, you've got 10 questions that can be answered. If you connect those chunks somehow, If you look at, do a pairwise comparison across all the chunks and say, okay, how are these two things related? Every time you do that, you've created new information. It's not just that you've related them, you've actually created new information at that point. And now the value that's there ends up being squared. Now you've got if you've got 10 chunks and you've got them all connected, and this is, in loose scale here, if you have a fully connected graph, the upper bounds of all the connections, all the extra information that's possible, ends up being the square of all the values that you started with. So if you had 10 chunks, you now have 100 things you can ask about those chunks just by thinking about how all those things are related. If you take that process one step further and take advantage of all the connections that are there to describe all the way that now you've got one-to-one pairwise connections, now you can jump out a little bit and actually say, okay, never mind just one-to-one. What about multiple ones and how those are connected and what does that mean? That leads to yet another explosion. And now it ends up being actually exponential. This is the classic network effect that happens with graphs, the dynamics of graphs, that if you think about the upper bounds here, if you went through all of the possible connections, if they were a fully connected graph and you looked at all the subsets of the graph that were possible, you'd have an exponential number of additional answers that you could give based on the original 10 chunks. So you start with 10 chunks, now you've got potentially an upper bounds of 1,000 chunks or 1,000 questions that could be asked of those original 10 chunks. This describes between these three different scales the entire scope of investigation and approaches and techniques within GraphRAG. The big, umbrella of GraphRAG all explores how we can take advantage of this information space, all these different ways of looking at data, composing it together in different ways to actually have different meanings about it that answers different user questions. Simply by connecting them, the upper bounds ends up being huge. And even if you don't hit that upper bounds, if you're somewhere, of course, let's say it's not a perfectly connected graph, it's, maybe half of that. Even so, the exponential nature ends up meaning that the potential number of answers is huge. And if you're doing it through the connections, not just random subsets, which, effectively here at a fully connected graph, it's any possible number of subsets. If you're using the graph for actually deciding what the subsets are, that the graph connections themselves have semantic meaning. So the subsets that are connected together ends up also having meaning of things that are related together. So GraphRAG broadly ends up being, just retrieval augmented generation, where the R is a graph. It does include being able to do vector search, but you can take advantage of many different indexes because we're just normal databases, and every database these days has vector index abilities. You also have geospatial indexing. You can also do full text searches, all those normal kinds of things. And what's lovely is that you can start with unstructured data if you want to, derive a graph from that. And you can think about the graph that's derived from that almost as a way of distilling the essential facts about the loose prose that's there. But once you've got those entities, you can also then start to connect them. How are those entities themselves connected to each other? The same dynamics that we went through on the chunks and trying to pairwise do the chunks. If you pull out the entities within the chunks, so if there is more inside of the chunk than just answering a single question, pull out all the relevant parts, connect all of those as well, you get that same kind of explosion over time. So it's a massive kind of surface space for questions to be answered within the data structures. And because of the graph nature, it's a normal database, you can very happily have unstructured data and structured data mixed in together. Once you've done all these different things and maybe added a couple extra layers on top for like having, let's say, a semantic representation that spans all the different representations inside of the graph, you have a very broad level of patterns available to you. But because this is all composable, you can start small, you can start with just vector search, and then as you add more data and as you start to realize connections within the data, you can augment that vector search. You can start to add in some structured data over time, add that back as well. Maybe you use the structured data for guiding extraction from the unstructured data in the first place. And one bit at a time, you go from just being able to answer whatever mirrors a user's question in a vector similarity search to get a chunk that may or may not have the answer, to better answers in a broader range of answers overall. The most simple possible GraphRAG that you can do. Actually, there's maybe one step even simpler than this if you directly went chunk to chunk relationships, I guess. But this would be the first step that I would usually take after doing some chunking. The next thing that you usually look to is that you do named entity recognition. You go through the chunk, you try to find, you ask the LLM, you work the LLM, or there's other techniques, but typically you prompt an LLM saying, hey, given this chunk, can you tell me the people, places, things, other things that are interesting for your particular domain inside of those in the chunk, and let's pull those out as entities. And for every entity that you find, you say, okay, well, what other entities were here? How are they related according to the chunk? Or how are they related to other entities from other chunks as well? So maybe they're similar entities, maybe they're entities that live in the same location or something. And so you can find connections amongst all the entities. One of the reasons that you do that is not just for the fun of having more connections and having created a graph, but there's value in that graph. And it shows up when sometimes users are asking questions and they're not just looking up information. They're not like, oh, I know what the answer to this is. Oh, remind me, what is the capital of France? It's usually that people don't even know what they're asking about. If they're asking a genuine question of inquiry, they may not know exactly how to phrase their question. And this is one of the challenges with the simple vector search is that the vector search will find chunks that reflect the phrasing of the question itself. And so if there's not a good mirror of the answer, because the answer doesn't precisely answer what the user is asking for, because they didn't know what to ask, then they won't get the right chunks back that maybe answer that. So in this example here, the suggestion is that, like, let's say that, chunk two mirrors the user's question really well. And so that's the chunk that comes back, but it's insufficient for answering the question. Just by taking one step out through to other chunks that are related, have kind of common entities have entities in common. So you go from chunk two out to the entities that are attached to it, and then the entities that are related to that, and then over to those chunks. So you're going one layer of chunks out through the entity network. You've already got a much richer context to answering the user's question. And you've got two options for how you could then give the context to the prompt in answering the user's question. You could either take all of the chunks and try to summarize those, or if you've got a big context window, you could take all the chunks raw data, pass all those in. Or you could take advantage of just the entities themselves and how they're related being the distilled information for the user. And you could use that for actually packing the context that you put into the prompt and generate a user's answer. So you have, even just with this setup, three different levels of access to that are possible. And you could rank those. So you could come up with each of those, rank for which one you think is the most appropriate, and then actually use that for providing an answer to the end user. Okay. And this is a bit of a whirlwind tour, but so I'm actually come all the way back around to what we've been doing on OPEA, and GraphRAG on OPEA. The example that we have, that uses Neo4j on the OPEA framework goes through doing what's called query focused summarization. So actually, if I go back to this slide for a second, the idea of query focused summarization is to do exactly this setup first. You start off with some unstructured text and you extract some entities from that. You get those entities connected to each other, and that creates a network that connects all of the chunks together, and it connects obviously all the entities to each other as well. And there's this analytical approach available inside of graph theory, where you can do community detection. And there's a couple different approaches for this. You can pick one that seems appropriate for your domain, and you can try different ones, of course. And the idea is that, like, all these entities somehow have a reason for being connected to each other. And when they're connected to each other, they end up forming, when you look at them visually, they're usually kind of clumped together like this. You'll see a little group of entities over here that are very well interconnected to each other. And they might have some loose connections over to this other area over here. And so there's this notion of doing community detection where you actually realize that for whatever reasons, according to the connectivity of the network that has been formed, that these chunks over here, the entities from those chunks, are very closely related. And these other chunks over here that are in this kind of ball of tightly connected, part of the graph is a separate community. And if you think about those communities, that those are, kind of broader topic areas, The idea of query-focused summarization is to say, let's take those topic areas and assume that that's going to be a broader view about the specific chunks, create summaries of those, and then on different levels of communities, at different granularities of community, you can decide, how big or how small you want communities to be, run a summarization and also do a vector embedding on the summarization, and then offer that as yet other access patterns for finding the best answer for a user. So in this example that we have running on OPEA, that's what we've basically done. It goes through doing an entire data preparation pipeline that pulls in the unstructured data, does the chunking, does the vector embedding, and that gives you kind of a local access for finding answers that are very fine-grained, that like directly have reflected answers inside of the chunks. It then does some named entity recognition. It does this community detection that's finding the clumps within the graph that belong together, find those communities, do a summarization of those communities. That ends up being what's called the query-focused summarization. And that gets you global content that spans multiple chunks that's available then for answering questions. This is what the full kind of architecture ends up looking like. There's two big components to it. There's the user interface, which has, kind of standard components for just managing the user's input query. There's a UI server that manages that, but it's also possible for the user to have pass data into the UI server when this is the kind of the pink lines on this diagram here. If data is passed in to get processed, that gets passed over to this data ingest pipeline over here. And it continues from the data preparation microservice, which takes advantage of the LLM and the embedding service, and also the graph database for creating both the chunks and also the vector embeddings, but then also this connected graph and then a summarization of these communities within the graph. After this data preparation is all done, any user questions that flow through the yellow arrows here go through a RAG gateway that then gets handled by this retrieval microservice, which also interacts both with the embeddings for, like, of course, embedding the user's question, and then interacting with Neo4j and the vector index on Neo4j for actually doing some of the lookups. We don't at the moment take advantage of doing any kind of fan out pattern matching around the graph as well, but that's an enhancement that we could add. And then, of course, it uses all that to be passed back to the LLM to produce an answer at the end. Turning all the way back and looking forward about where we're going. So if I talked at the beginning about this general idea about composition and also this kind of scale of the different levels of how graphs form when you start with unstructured data and even structured data and how you can kind of evolve it over time, and this upper bounds of this crazy, exponential growth in the surface area of the information that you have. There's so much really fascinating research going on these days. A lot of course, is focused on agentic approaches. And so now these days, we're talking a lot about agentic GraphRAG, which both for us means two things. Means within the RAG pipeline itself. So when you're just retrieving something from Neo4j, that there's an agentic component to that, but also that we participate in the overall agentic flow. So that in the graph planning itself, I'm sorry, we use the graph for doing planning. When the agent is trying to figure out what's available, we can tell the agent, by the way, here's all the data that's available. Here's all the different ways you can access it. So we can actually dynamically, based on the data, have data-driven tool definitions that are then available to a particular graph agent that knows how to access those, but then also that the reasoners can actually look across that and come up with a plan for deciding which of these different things they want to use and how does this combine for other things, and then also using the graph for memory along the way, so that the plan that it's coming up with for answering a particular user's question can get saved to that memory, referenced later, so you can learn from your previous successes. And all along here, there's an amazing number of papers that are available. We've been collecting these papers at a website called graphrag.com. Every time that we try to read through the papers, we try to understand really what the cores of what's going on there and distilling the fundamental design patterns and the access patterns involved. And we're trying to document it there. It is a labor of love. We're a little bit late usually in trying to update the website itself because there's so many papers coming out all the time. This here is a very valuable listing. You can also find a listing of the GraphRAG papers that we've been reading on our Hugging Face space. If you want to keep up with the latest and greatest of all this stuff, that's the place to look. If you start to look through these sites, you'll see where everything is headed. This is one of the challenges working in Gen AI overall. It is all moving so fast. It is really hard to keep up. This is really just a taste of like where things are going. If you want to, learn along with us as we're learning in public, it'd be great to have you along. If you want to contribute some papers, you have some papers that you've come across, please let me know. That would be amazing to get those kinds of contributions. But don't feel that you need to keep up with all this stuff. All this stuff is like the looking 6 months ahead about like what kinds of features you're going to end up seeing either from us or from our partners or from other people out in the open source community. There's so much amazing work going on. So this is almost like a sneak peek into the future, I would say. Okay, that was I'm not sure how I'm doing on time. I can't